Good afternoon, everyone. Thanks again. Welcome once more. This is the last talk of the Science and Data Miniconf. And our next speaker is Dr. Robert Layton, who has a PhD investigating cybercrime analytics and is a data analyst working on text problems for business. Please welcome Robert and the talk, Learning TensorFlow.
Hello, thanks for coming. So probably one thing to know, I'm a shameless self-promoter, so website. So yeah, today I'm going to overview the TensorFlow library. Many of you have heard of it, and that's probably why you're here. I'm going to make a prediction now, and it's on camera, that next year's mini-conf on this topic will have quite a number of TensorFlow talks. I'm going to guess half. Just as a bit of background, when TensorFlow was released late last year on GitHub, within a day it had more stars than what the scikit-learn project has. And scikit-learn has a very long history and very well regarded within the data mining space. So TensorFlow is big. It's very popular. It's very new. But what is it? How do we use it? And why would we bother? So my name's Robert, and I wear quite a number of hats, but for this talk, at least, we're just going to have a look at the TensorFlow library. This is a very introductory. I have to apologize. I have tried to get it to stop doing that, but it's not listening. So I've just kept moving the mouse randomly. So it's an introductory talk into TensorFlow. So this is not a deep learning talk. I'm happy to take questions and then just delegate them to someone else later. I know a little bit about deep learning. I'm not an expert. So I might do a poll later and see if anyone actually is a deep learning expert. Do that just before questions. I've also got a book. It doesn't have TensorFlow in it, but it has some related material. So buy that, please. So what is TensorFlow? So when we're in Python, as we all know, it optimizes programmer time. So we can do something in a day of Python that might take us a week in Java. It might take us a very long time in C. So Python's built from the ground up to really optimize programmer time. And I say that over, skipping over a whole bunch of Python history, but that's the idea anyway. So when we want to do something like take a long list of numbers and multiply them all by 2, Python's not actually good at doing that. The reason for that is that a list in Python is just a ordered collection of things, and as far as Python's concerned, it doesn't care what those things are. So when we want to multiply them each by 2, it asks each of the things, how do I multiply you by 2? So that's the reason why Python is slow for numerical processing. So when we want to do that in Python, instead of staying in Python land, we move to NumPy land. And we create a NumPy array object, which is represented at the low level with quite a C-like interface with a number is a number, or specifically an integer. It specifically has this many bits to represent it, and so on. So when we now ask the question, I want to multiply each number in that list by 2, we can actually use more optimized algorithms to go through and say, okay, each of these is a number. I know how to multiply numbers by 2. Let's just keep reusing that operation the entire time. So we use NumPy to do numerical processing in Python, and that allows us to do this processing much faster. The problem with using NumPy is that when we do an operation, we get back a Python object. So when we do our next operation, we then have to transfer our operation back into NumPy land. And most of the time, this doesn't matter. But if we want to do a Python-based operation on that list, we have to convert all those numbers into Python things, do a Python operation on that, and then do our next step. So that to and fro becomes quite expensive. So as a broad rule, whenever we have NumPy code and we want to make it go faster, we push all the operation down into NumPy land, and we stop coming back up to Python land all the time. So why did I just bother saying that? TensorFlow basically lets us identify all the operations that we want to do, and then just say, okay, now go do all of those in TensorFlow land and just optimize all of that. So, so TensorFlow is a library for creating a computational graph. There's really two phases to a TensorFlow application. The first phase, we define the graph. We say, you're going to get data of this format, you're going to do this operation to it, you're then going to move over and do this other operation to it, you're going to pull this other data in and combine it and so on. But we're not actually doing any work there. And this is lazy computation. There are quite a few ways of doing this in Python and in other languages, but TensorFlow is one of those options. But we're creating this computational graph. And then at a later stage, we say, okay, here's a graph. Now here's some data, and I want you to go and actually work out what the result is. So by first creating that computational graph, we get to a point where all of those operations can be done in TensorFlow land, and it no longer needs to ask Python what to do next. So TensorFlow itself is C++, but it's I'm going to say official. I'm not from Google, and I really don't know if this is true. Its official language is Python, to the point where the Python APIs actually have more functionality than the C++ API. So you can do just C++, but why? So Python's the main way of using TensorFlow. But all the heavy lifting is done with much more efficient code. So the basic idea of TensorFlow is in that second bullet, or the first of the second lot there, computational graph, build a graph, then run it later. This gives us the advantage of doing lazy computing, which is almost always a good thing, unless you're debugging. And the other thing that this allows us to do is it allows us to, maybe not at this stage in TensorFlow's life, but at least in the next year or so, be able to do things like transparent distributed processing, moving different operations to different devices, such as GPUs and CPUs. And because it's a computational graph and not code, we can reference the graph and say these things are better done on a CPU, and these things are better done on a GPU. And I'll get to that a little bit later. It allows us to focus on the algorithm, not implementation. And if you haven't written a program with that mind frame before, one thing you may have done that's similar is write an SQL statement. So with SQL, you're not actually telling the database engine how to go off and collect the data. All you're saying is, I want these columns from these tables where this condition is true. MySQL or Postgres will then take that wish and then turn it into operations. And if you've got a distributed database server, like multiple databases, data collected over different spots, it will work out all those details for you. You basically just are given a query and say, I want you to give me this information, and then it works out the details. And TensorFlow does a lot of that for us. TensorFlow is still quite new. It has a very large and very quickly growing number of libraries. I think when I first did this talk, there were only a few libraries on GitHub that actually use TensorFlow for anything specific. Now there's dozens coming through every week on some of my alerts. So the other thing I should point out is that TensorFlow is not a new thing. Like, the concepts behind it, this isn't like drastic groundbreaking stuff in terms of computer science. It's not even groundbreaking from that respect in terms of Python, because we have the Theano and Torch libraries, which do pretty much the same thing. So if you've used Theano or Torch, you know everything what I'm telling you about. The main reason why TensorFlow is a thing is Google uses it. Google basically runs on it, or is transitioning to a point where Google will run on it. And that also means that it's got backing by one of the most powerful companies in the world. So it'd be highly unlikely that it's going highly unlikely that it goes away anytime soon, and it's going to have a lot of resources thrown at it, both officially and unofficially, because of its brand name recognition. So that's why I made that prediction. Next year, this will basically be the TensorFlow miniconf, but we'll see what happens. I'm on record now. So this is an example graph, stolen or borrowed from the documentation. We basically see down the bottom there's an input, and then the lines basically say, move this input up through this operation, combine it with this other data, and so on. And we get to a point where all of the operations, including calculating the accuracy, for instance, in the training accuracy, they're all operations on this computational graph. So we don't need to move away from this graph to train it. We don't need to move away from this graph to evaluate it. And we don't even need to move away from this graph to do the final prediction. So everything here stays in TensorFlow land, which is a good thing. So here we've got a very, very basic example. So we import TensorFlow, and it seems to be that TensorFlow has taken the two-letter TF. So in the same way that NumPy is NP everywhere, TensorFlow is TF. So in the first line, we create let's just call it a variable, x. I'll get back to the distinction a bit later, which is going to be the value 35, implicitly an integer, and we give it a name x. That name there is optional, but really useful for debugging. I'm not going to use it anywhere else in this talk, but it's a good habit to get into. We're then going to say y equals x plus 5, but then if we print it out, we don't get 40, we just get this operation object. To actually run that, we create a TensorFlow session, which connects to the back end. We pass in at least the part of the computational graph that we're interested in. So we're saying, we want y, do whatever you need to do to get me that value. And this is the other advantage from, say, this graph. So this whole graph here, we can run the whole thing, but if we're only interested in a small part of it, say, for instance, we just wanted to calculate wx plus b, we could ask for just that value, and it will only do the computation necessary to get to that. So that's a very, very basic example. And then once we do that run, that gives us our result. So you'll see this pattern a few times. Now I'm going to use this image. Images are quite useful in this regard because you can read them in and they convert to useful large NumPy arrays. So we can get a data set to work on that actually means something. So I'm going to use this image. We read it in with matplotlib. That gives us raw image data, which is basically a NumPy array. It has about 5,000 rows, 3,500 columns, and 3 color depths. So it's a 3-dimensional NumPy array. We create a variable. This is different to tf.constant, but I'm getting to that. Pass in that raw image data. We then initialize all the variables, and I'm going to be honest here, I don't know why. I don't know why we have to do that step all the time and why it can't be just part of running the graph, but it's necessary. So we create our variable x, which is going to be our raw image data. So we go from NumPy object into a TensorFlow object. We then create a transpose operation, which is the first under the context context manager. So that's our transpose operation. We're going to take that x and permutate the axes. So we basically just swap in the first and second axes, turn that sideways. So that's our transpose operation. We pass that into session.run, get the result out, and then I just plot that here. So you can see that we've turned that image sideways. Okay. So going back to that variable or that constant, what are they? So there's actually a third one, which is called placeholder. So constants and variables, I really should have reordered these. Constants and variables are for when you have values. Placeholders are for when you don't. So with regards to building the computational graph, you want to be able to build that graph and then push data into it later. And then that gives us all the advantages TensorFlow has. So we use a placeholder for that. So in the first example, in cell 4, we create a placeholder called x. It's going to be of type float, so we don't have any data yet, so I can't infer type, but that's actually quite important. And we say we're going to pass in 3 of those. The size is optional, but does help. We then create a basic operation, y is x times 2. And then we pass in y into session.run and print the result. The difference between this and previous is this feed dictionary. And what we're saying with feed dictionary is the values for x are going to be this list here, 1, 2, and 3. So we've created our computational graph, which is all the steps above the width. That was creating the computational graph, and then we run it later. We give in our data, which we didn't even have at the start, later. And then that gives us our result, each of those numbers multiplied by 2. Where it starts to get a bit more interesting is placeholders can be multi-dimensional. So in this case, we have a 2-dimensional placeholder. The first is none. The size of the first axis is none, and the size of the second axis is 3. So it's a something by 3 matrix, and by passing none, it's arbitrary size. And you'll probably see that quite a lot with machine learning because we're going to pass an arbitrary number of samples in with 3 features or something like that. So that's sort of the common, or that I think it will be a line that you might see quite a lot. Then from that point on, it's all the same except for our data is now a 2 by 3 matrix. So this could be a 3 by 3 or a 4 by 3 matrix or so on, and the code will work just fine. Getting back to our image, here we create a placeholder which is a num by 3. I could have worked out exactly how many pixels there were. I probably should have done that, but this will take an arbitrary image with 3 color depth, or 3 levels of color depth, and then reverse them. The reverse operation here has a weird syntax, basically saying reverse the first axis and keep the other 2 axes the same. I'll get back to that because it annoys me. So we create our placeholder, and then in the first line under the width, we then say the image placeholder, give it this raw image data, and that's the data we loaded in from Matplotlib earlier. And then I printed the shape, but then I showed the image. So in this case, we reverse the first axis, which is rows, flipping the image over. Going back to the true, false, a lot of something I run into a lot, and maybe it's just me, is I sort of automatically convert a NumPy operation into a TensorFlow operation. That won't work. TensorFlow have a lot of operations that do similar things to NumPy operations, and they have somewhat similar signatures, but at the end of the day, you really need to check the TensorFlow documentation for what those variables are, because, for instance, I would have expected just to pass in a 0 there to say reverse the first axis. That's NumPy thinking. TensorFlow thinking, it actually does this quite a bit where you pass in values for each axis. And we'll see that in a minute with reverse sequence, I think it is. You end up giving it a value across each axis, and it does that operation all at once. So yeah, create a placeholder, do an operation on that placeholder. So for the first 2 lines, we've only created a computational graph, and we don't even know what the image is yet, and then run it later by passing that image in. Constants, you use these for values that don't change and values that you know up front. So in this case, we did know the image up front, so we can create a constant. We don't need to pass any information like the size of it or the type of that. That's all inferred. You can pass it if you want to. And then we do a slice operation. This was the other case with the axes. So in this case, we do a slice operation on the image. The first list there is the starting position across each axis, and the second list there is the size, with -1 being go to the end, which is not like that at all. That should probably, I don't know, being picky here, it probably should be something like 3,000 none or something like that. But yeah, so this is a common pattern. You give it the data, and you give it, for multi-dimensional operations, you give it what to do across each of those axes. which is probably a bit more efficient, but it's a little bit annoying as well. But apart from that, everything else here is fine. The only difference really, apart from the exact operation between this and the previous, is that I used a placeholder here and gave it the information later, and I used a constant here and gave it the information straight away. So the information was included as part of the computational graph in this point, which at least normally in this case is not what you want, but so it is a useful idea. Variables are placeholders for things that will change later. So in this case, this is a standard linear regression model, AX plus B. I'll get to the training in a minute, but sorry, there we go. That's the key line there, the W. So in that case, those are our weights into our algorithm. So that's a variable. So we're going to learn those weights. So the idea here is we know what the model is. We don't know what the particular variables, the values of A and B are. So we're going to learn those by giving it some data from that model, and then it's going to go off and try and predict what those values are. So W is a variable. It has two values in it, but those will be updated as part of the learning. Y model is an operation on W. So at this point, no work actually gets done, but it just identifies it. That's the relationship between those values. And then later on, we're going to pass in X and Y values, which are represented there as placeholders, so that later on we give it those values. Now, common with variables is training them. So we've got a gradient descent optimizer. This is basically a subgraph that you can include in your graph to do the training of particular variables. So someone else has written that for you. You could re-implement it yourself. It's just it's just a graph. And then its job is to minimize error. And error, if you go up 2 lines, is the square of the difference between the model and their given values. So that's a TensorFlow tensor. And then it's up to gradient descent optimizer to take that, work out how to minimize that. And how it minimizes that is done by changing Y model, which is done by changing W. The advantage of this over, say, something a bit more direct, or say Python land, is that because error has information about how it's created, because it's a relationship between different variables, things like gradient and derivatives can be calculated where possible. So you don't need to pass in derivatives and stuff like that. Because it knows those operations, it can do smart things in the background. So those are the secret variables. So we're now AX plus B, those are the values. So we open up a session, then we do 1,000 training loops, and there's other ways to do this with convergence and stuff like that, but in this case we just do 1,000 training loops where we give it random data, so random X values. We pass in, we calculate the actual Y values from those X values, pass those in as our feed dictionary to the X and Y placeholders, and then do that training operation, which was that gradient descent optimizer. So what it's saying is, here is some data, try and find the A and B values that best minimize this. And then we just keep doing that. And the more this runs, the better, or the closer it gets to the actual value. So we had 2 and 6, so there, and it's estimated 2.2 and 5.8, so pretty close. I would have expected that to be a bit close for such a simple example at 1,000 iterations, but you never know. Now, one sort of hidden feature of TensorFlow that I found really, really useful when I was learning TensorFlow is PyFunc. And PyFunc, which is in the last line of cell 12, basically takes a Python function and turns it into a node of your computational graph. So that if you know how to do it in NumPy, or you know how to do it in Python, but you don't know how to do it in TensorFlow, or there's not the function to do it in TensorFlow, this can help you cross that hurdle so you don't spend an hour looking through the documentation to work out what that step is. So I found this really useful to sort of build computational graphs along these lines, and then swap those out with actual TensorFlow operations later. So in this case, we have a game of life implementation. So update board will take a game of life board and then update it according to the rules of game of life. Jake's website there has a really small one-liner which uses convolution to work out how many neighbors a cell has. So feel free to ask a question if you're not sure about a game of life, but I'll skip over those details for now. But basically, we take an x, we update it according to some rules, and we return another x. But that's all done in NumPy or SciPy. Convolve2D is a SciPy operation, so you can just pretend that I didn't actually realize there was a convolve operation in TensorFlow when I wrote this, and that's actually what happened. So we can replace all this with a TensorFlow operation, but this is a very good example, I think, for PyFunc. So we create that board update, which is a PyFunc. So it creates that Python function, turns it into a TensorFlow node, and puts that on our computational graph. And then from that point on, everything else is pretty straightforward. We create an initial board, and TensorFlow have some random generators, so you don't need to create a NumPy random and then put it into TensorFlow. And then all the rest here is just running that cell and then doing a matplotlib animation. So I'll show you that. See if I've made enough sacrifices to the demo gods. So Python. So in this case, this is a very large game of life operation. It's all being done on the GPU, and I'll get to that in a second. So this takes an x, which represents one of these states, updates it according to the game of life, and then shows the next step. So that's very large. That's 2,000 by 2,000, which would hurt other systems. But in this case, it does quite well. And that was done using a PyFunc, so to represent that part of the graph. The other thing you might have noticed is all this output here, which is the TLDR is basically, it was running on the GPU. Cool. All right, so let's get into a little bit of machine learning now. So you might have heard of a package, or you might have heard rumors of a package called skFlow. That doesn't exist anymore. It's now TensorFlow Learn. And for someone that has a website called Learning TensorFlow, that's actually given me a good boost. I swear I didn't do that on purpose. But TensorFlow Learn is basically wraps a whole bunch of learning algorithms that are implemented in TensorFlow and wraps them according to the scikit-learn interface. So that if you know scikit-learn, you can just basically copy your scikit-learn code and just start doing stuff in TensorFlow. So I've got that. NumPy is the scikit-learn, what TensorFlow is TensorFlow Learn. And if you've done any scikit-learn before, then this will all look familiar. I had a bug which meant this didn't work up until about 3 hours ago, so I was able to fix that. I'm pretty happy. But basically the idea here is that we created a classifier, which is our second last line, which is just the shell of a classifier, and then we fit it with some training data, and then we use that model to do prediction, and then we can see there the output there. So in this case, if you're interested, what we did is we load the digits data set, which is handwritten digits for, and the job of the machine learning is to work out what the digit is that's been handwritten, whether it's a 1 or a 2 or so on. So in this case, it's able to predict when the number is a 0. It's able to predict that with 98% precision and perfect recall. So it's a pretty good model. But that's a well-known data set. So let's move on to the GPU. So the example I gave before was running on my GPU. The reason this is a good thing is CPUs are quite smart. They have a lot of operations for doing things efficiently, but they're generally single or single-ish thread operations, so they can do one thing very well at a time. GPUs have a whole bunch of really dumb CPUs, if I want to gloss over a lot of technical details. So GPUs have, a modern GPU will have thousands of little processors running, but they all do one thing, but they can do it across a whole data set all at one time. The good thing for us as machine learners is that that one thing usually involves operations on matrices, which is like 90% of data mining, so that's really good for us. So all the people playing video games have really helped the field of machine learning quite a lot. Cool. All right, so all of this is going to look quite familiar to you, except for the width at the top. So in this case, we set a device name, which is the first CPU. We then create a context manager, and we say, for these operations, do it on that device. Yep. So do those operations on that device, and then the rest of it is pretty much just running that. There's a session config in there if you want to have a look at the code later. So in this case, we run this dot product and sum in on a CPU, and the bottom line there took nearly 12 seconds. And in this one here, we just changed it over to the GPU, and it took 1.3 seconds. GPUs are really good at those types of operations. But unfortunately, not all machine learning operations are those type of operations. So sometimes you have to switch. And TensorFlow gives us that ability. Run some nodes on the CPU, run some nodes on the GPU, combine them later. Keep in mind that switching is expensive. There's also Keras, which used to work on Theano, still does, but used to. But now it's also TensorFlow enabled. So Keras, in that case, I'm just doing a one-hot transformation. Keras can be pip installed, the only real thing that you need to do is create a JSON file that has the backend as TensorFlow. So that's all I'm doing there. So that just tells Keras to use TensorFlow instead of Theano by default. And then at this point, we're actually doing creating a neural network by using a sequential model, adding a whole bunch of layers to the neural network. I'm deliberately glossing over a whole bunch of details. I was given extra time, and I'm still running over time. And then just fitting and training that. So that's Keras. So the good news there is if you want to do machine learning with TensorFlow, you don't need to know all the plumbing details. There's really good libraries popping up, and over the next year or so, we're going to get a huge proliferation of TensorFlow across in the back end of pretty much all machine learning in Python over the next few years. So that's my talk. I'm Robert Layton at those things, and feel free to drop me a line. I'm not very active on Twitter, but Twitter pings my email, which pings my phone, so you'll still get to me. Thanks.
Thank you, Robert, for this talk. We have some time for questions. I'd like to see raised hands. And I have one first question is, how much does the programmer have to think about where they want to perform their computation? How much do you have to say, well, I have a bigger GPU, a smaller GPU, I have more memory, when you do this kind of scheduling?
TensorFlow will tell you when it can't do an operation on a GPU. So if you want to be empirical about it, the workflow is basically try it on GPU, and if that doesn't work, put it on a CPU. But I don't think, at least for most of the stuff most of the people here are going to do, I don't think there's a huge amount of thought that needs to go behind it. But then there's those 1%ers that really need to care about it. But I think you'll know if you need to care about how much memory you're moving around and stuff like that. Yeah.
So, who had a question? So 2 questions on this side, and I'm going to let you go first.
Since you're building like a large computation graph, then running it as like a single step, what happens for debugging that when it doesn't do what you expected it to?
Yeah, so debugging machine learning is a hard problem, and I'm going to pretend that's a different question. Debugging the TensorFlow part of the machine learning process, if you give your variables names, and by default, they'll get a name corresponding to name of the variable you assign to it. So, so in this case, the board here is a little bit redundant. It'll tell you that there's some problem with the board variable. But if you start giving names to things, the stack trace will say variable x0 was expecting data of this format and it's not of that format, or something like that. So if you get into the habit of having names, and I've lost the name of it, but there's also, I'm going to call it a context. So you can open up a context and all variables defined within that context get that prepended. So you can say things like, this is the layer 1 context and this is layer 1's weight. So then when that prints out in the stack trace, it'll say layer 1.weight. So if you get used to naming them, that'll come out in the stack trace and make finding those much easier. Yeah.
I've sort of got two questions. So the first question is, if each node or tensor in the graph is for an operation, is that analogous to sort of like a scikit-learn pipeline? Like, is it for the workflow?
Yeah, it's very similar to that. Yeah, as I said before, like, this is not groundbreaking from a theoretical point of view. It's probably more groundbreaking from a practical point of view. But because of the resources behind it and just the general efficiency of these things, TensorFlow is probably in the lead in many regards there.
And how does TensorFlow compare to Theano in terms of ease of use and performance?
If you're using Keras, it's the same. So you just switch the back end. Actually, it's a little more difficult because you need to change the default. But in terms of the actual plumbing, like if you want to do it yourself, I think TensorFlow is a little bit easier, but it's more recent in my memory, and I've had a bit more experience with it. So yeah.
So I'm going to ask you the question that I got asked, which is, so is all machine learning in Python going to be done in TensorFlow next year or not? And if not, why?
Okay, so I think the large majority of, at least, we're going to hit a tipping point where new academic research is going to come out with TensorFlow. But if you think about how much academic work still comes out with very old languages, then it's a very slow process. But I think TensorFlow generally is the direction to take. So if I was back in my old role as a machine learning researcher, I'd probably start using this for my research and delivering code with TensorFlow. Yeah.
But what about limitations?
Oh, okay. So limitations of TensorFlow. Yeah. I suppose the main limitations to TensorFlow is it doesn't scale down well. So this is for, you can do your standard iris data mining problem with 150 samples. You can definitely do that with TensorFlow, but you shouldn't need to bother. Because it's in memory, you're just adding a whole bunch of overhead that you don't really need. But that said, when you get down to that size, a little bit of extra running time doesn't really matter. So you can probably afford that overhead if you think your problem's going to grow. Yeah. Yep.
I'm just wondering, if you've got a data set that you want to work on that doesn't fit in main memory, is there a way to iteratively feed it into TensorFlow?
Yeah, so if you think about, so this learn linear model, if we change the size of this from the current 1 to just enough to fit in memory, then this will run. And then the next time, X variable will be overridden with new data that's just enough to fit in memory. So effectively, we have a training data set that's too big for memory. But that's the basic way, chunk it. And just pass those chunks in one at a time. Yeah.
We have time for one last question. And
Hi. That's pretty exciting that I can just select which device, i.e. GPU, rather than having to learn CUDA or OpenCL myself for certain parts of the problems that I face. So that's pretty exciting. Which GPUs does it have better support for? Is it going to run better on ATI or on NVIDIA? Does it use a mix of OpenCL or CUDA depending on which device it detects? Or?
Yeah, so my experience has only been with CUDA, and I'm pretty sure that is what's supported. I haven't seen anything really that talks about graphics cards other than NVIDIA. And I think, and I'm being deliberately vague here. I think you need a compute power of 3 or I think the expectation is that your graphics card will have a compute power of 3 or higher to run as the GPU in TensorFlow. I think older ones will work, but may not be well supported. But yeah, you say you don't need to learn CUDA, but you need to learn to at least install it, which is a little bit painful. Yeah, cool.
Thank you, Robert. And we have, I'm going to give you on behalf of PyCon, a mug.
Fantastic.
It has the flying tram, the symbol of Melbourne, and of this year's. It's on the T-shirts also.
Yeah.
And thank you very much.
Thank you.